Welcome back, welcome back, welcome back. I'm Miss Lisa, and this is my YouTube channel where I talk about science and math. This class is physical science, which is primarily designed for homeschoolers. But if you want to listen, you like the way I explain things, come on in. We're going to be talking about electromagnetic waves today, which if you're doing this as a class, is chapter 12 in your book. We've been talking about waves, and that's why I have compression waves and transverse waves on the board behind me. I want you to like, share, subscribe, because I am trying to get 1,000 subscribers so that making these videos is easier for me. Bottom line, I don't mind doing them. I like blessing the homeschool community, but it's very time consuming to upload them. If I get 1,000 subscribers, I can just do it direct. It'll be easier. And so share them with your homeschool groups. Tell people about them, that this is free math and science at the high school level. You just have to buy an older a used textbook. They're pretty cheap off of Alibris, eBay, and Amazon. Usually you can get them for less than $15. So it's pretty cheap for a high school science or math class. And so I've got 4 math classes and 4 science classes, and I'm glad you're here. I love physical science, and I like talking about it. So we're going to talk about something that I think is very interesting. It's called electromagnetic waves or electromagnetic radiation. All right, so we've talked about light waves and sound waves, and they are especially sound, and about how it moves on Earth. And sound, to move around here on Earth, it moves through a medium. If you are out in outer space where there is no molecules, no gas molecules, you wouldn't hear a sound. So all of those sci-fi movies where things are blowing up in space and making all this noise, in reality there would be no noise because there's no molecules to carry the sound with the compression waves. I'm pointing to the compression waves back there. So we're going to talk about a kind of wave that can go through space, and it's light. Light on our Earth is going through molecules, so it can go through molecules, but it can go from the sun to here, from the stars to here, and it can go where there are no molecules to carry it. So your book goes into quite a bit of trying to explain it to you, more so than other physical science books usually do. But where it comes from is there is a relationship between electricity and magnetism. Electric things like a charged particle, like a proton, an electron, things like that, can make an electric field. So you can think of that. Magnets make a magnetic field, and we've already learned there is a relationship between the two, that if you move magnets near a wire, that you get electricity. So there's a relationship. So the magnetic field and the electric field sort of produce each other, so they can kind of keep each other going. And they do this in transverse waves that are at right angles. It's like if you take 2 cards and you stick them together, that you get right angles. And you can see this in your book on page 356. Just know that the changing electric field causes a magnetic field, and the changing magnetic field causes an electric field. So they are, and they're perpendicular to each other in transverse waves. But what this is radiant energy. This is what the sun and all the other stars do, is they produce light. They produce radiant energy. And you know the sun makes light, but it doesn't just make light, it makes the entire electromagnetic spectrum, which you can remember by this: Ronald McDonald is very ugly, extra gross. Don't sue me, McDonald's. It's just a way to remember this. I like McDonald's. Send me some chicken nuggets with honey mustard sauce and one of those coffee frappes. But please don't sue me, because I'm using Ronald McDonald as a negative image here. So Ronald McDonald is very ugly, extra gross. So Ronald is radio waves. So this is not the sound waves coming out of your radio. It is the radio waves that are transmitted by the transmission tower for the radio that fly through the air at the speed of light and then are intercepted by your radio and then translated into sound waves. So radio, Ronald McDonald, microwaves, so the kind of waves that are in your microwave oven, Ronald McDonald, is infrared. This is has lower frequency than visible light, and it's heat. When you think of heat, radiation coming out, that's infrared. And then very visible light, Roy G. Biv, the rainbow. And then beyond visible light is UV light, ultraviolet. And that's what causes your skin to get sunburned. It can cause skin cancer. It's higher energy and it can damage cells. And then very ugly extra is X-rays. You can take pictures of your bones with it. And then gross is gamma rays, what turns Bruce Banner into the Hulk. But really, they're high energy radiation that can cause damage, but also it's used to treat cancer. It can cause cancer and it is used to treat cancer. So there are some uses for the whole electromagnetic spectrum. So we're going to talk about that. We're going to go, first of all, we're going to talk about all of these things. You have to remember, travel at the speed of light. Now, your book says that the speed of light is 300,000 kilometers per second. Kilometer is less than a mile, but you can kind of think of it like miles. I always use the physics definition that we use in the physics math, which is 3 times 10 to the 8th power meters per second. So I've memorized the speed of light in a vacuum at 3 times 10 to the 8th meters per second. Now, what do I mean in a vacuum? Light can slow down, light depending on what it's going in. And you know this because you have seen light bend. You've seen a straw, and as the light's going from the air to the water in your glass, and it makes the straw look like it's bent like that. Light can bend, it's diffraction. So you know that. And you've also seen when it rains and in the parking lot where people have dripped oil, and then you see these little rainbows in the parking lot, and then the oil, it's pollution, but it's pretty, that you will see, and that is caused by the oil causing the light to bend. Also, it is on the cover of the book that we are using as a lab book, this one. You see these bubbles are bending the light, and you're seeing the rainbows on the edge of it. That's all because of diffraction. That depending on what medium the light goes through, it goes at a different speed. It slows down. So light in a vacuum, that means nothing slowing it down, is 3 times 10 to the 8 meters per second. The whole thing travels at that speed. Radio waves, microwaves, X-rays, gamma rays, visible light, the whole thing travels at the same speed. Now, the next thing it talks about is that these have a frequency, and they might all travel at the same speed, but they have different frequencies. The ones at the low end, the radio waves, Ronald, they're bigger. And the ones at the gamma end, the frequency is more quick because the waves are tighter in, going up and down. And I think they show you that in your book. If not, I think it's in the other book. So this light that we're talking about, the whole spectrum, has some really interesting properties. One is that it behaves like a wave. And that's what you would expect it to do. You would expect light to be a nice little transverse wave. But the weird thing is it also acts like a particle. There was, in your book, it talks about that Heinrich Hertz in 1887 found that by shining a light on a piece of metal, that at a certain frequency, that electrons would splash out of it. And that didn't make sense, because if light is just a wave with no mass, how is it making electrons splash out like they have been hit by a particle? Well, later on, Einstein figured it out. He figured out that light has a dual nature. It behaves like a particle and a wave. And we see this in light bulbs. The electrons will be moving along, little electron particles. They hit resistance in the filament, and then they can become light and fly off as a photon. And it sort of makes sense that electrons are actual little things with a mass, that they would have a particle nature, but then the way that it can be transformed into a packet of energy, a photon that is related to it, sort of makes sense that that's a wave. The way they proved that that light also can behave as a wave is they put it through little slits. And when they put it through little slits, it spread out and it had interference. And so they were able to show, and then also they were able to show that it was a particle by having little paddle wheels shooting the light at it, and it had enough power to make the paddle wheel turn. So, and the electrons could splash out of it. So those were some of the early experiments that showed what Albert Einstein said was true, that light has a dual nature. It can behave like a particle or a wave, which is really weird. All right, now let's go back to the electromagnetic spectrum. It's in your book on page 360, and it shows you how as you go from the radio waves to the gamma waves, that the frequency increases, that you get faster waves in their frequency. So radio waves is the first one, and it is not what you hear. You can't hear radio waves. Radio waves are all in this room right now. I can't tell it's here unless I have a radio wave detector, which is radio. Then I can put a radio here. I can pull up the antenna and I can dial it in, and it would find the radio waves and translate it to sound for me. So radio waves are, the electromagnetic radiation is all in this room. There's radio waves, there's TV waves, there's all kinds of waves in this room right now, and there's light. That's more electromagnetic radiation. So radio waves are made by the sound transmission tower vibrating, which makes the electromagnetic radiation go out in all directions, and then you can find the radio by tuning in, and then your radio will translate it into sound waves. Now, microwaves are actually a kind, next. They're like higher energy radio waves, and they can make things vibrate. They make the water molecules vibrate in your food, and that heats it up. So we're used to those. Radar is another thing that radio waves are a type of radio waves used, and they're used for detecting things. It's used for finding objects bouncing off. Another thing that's used for is MRI. If you ever had to have an MRI, then look at your shoulder or whatever. It's magnetic resonance imaging, and it's using electromagnetic radiation, radio waves, in that spectrum for the Ronald McDonald radio microwaves, that they use that to find out what's going on in your body. So a lot of people have to have those. I've never had one. Hope I never do. Looks kind of claustrophobic having to get in that tube and have them shoot me with that stuff. But I guess I'd just have to do it if I had to do it, right? The next one is infrared, and that's heat. That is heat waves, infrared radiation. And it's used for imaging and things like that. The next part is visible light. Now, visible light is just a tiny sliver of this huge spectrum of radiation. And so it's really interesting to think about that we can see it. That supposedly eyeballs evolved to be able to see light that they didn't know was there. And eyeballs are very complicated to be able to take this light and transmit it into impulses to go into your brain. It's really shocking to think about. The picture in your book of the part that's the visible light is misleading how big it looks. I mean, it's just a tiny sliver of this whole electromagnetic spectrum. And we can see it. We're looking around. I'm seeing things right now. I'm detecting the visible light with these visible light detectors in my head. And the fact that all that works is shocking, is amazing. The next idea is that we're going to talk about is ultraviolet. This is beyond what we can see. Some animals can see it. Bees can see it, but we can't. Ultraviolet, it's beyond violet is the next thing. And it can actually hurt your skin. It's what causes sunburns, and it can cause skin cancer. I used to teach, and people will go to tanning beds and get tanned, and it's very harmful to your skin. And so I used to teach that, and I always would have kids go, Miss Blackburn, people should not do that. That is bad for their skin, and they should just be happy the color that they are, and not try to change their color with getting a tan. So that was always my advice, was passing on from some of my students. You should be happy the color you are and not damage your skin by getting a tan. But some ultraviolet light is actually good for you, a little bit of sunshine, because it helps you get vitamin D. And your book says that that's good for healthy bones and teeth. It is also good for your immune system. It's really good at helping you stay well, which is important right now with us having COVID. So UV light can also be used in things. They use it for fingerprinting, and it's also used to kill bacteria. The ozone layer is this layer of O3, and I had O2 up here, I don't anymore, but instead of O2, it's O3, and it's a layer that goes on the very outside of our atmosphere, and it protects our Earth from most of the harmful radiation from UV light. Most of it is deflected by that. Now, your book says some misleading things. I'm just going to be honest here. It says that the ozone layer is destroyed by CFCs, which is a chemical that does destroy ozone. The problem is it's a huge chemical. It's chlorofluorocarbons, and for chlorofluorocarbons to get all the way up to the ozone layer is almost impossible. It would be like suddenly a safe floating up to the ozone layer to destroy stuff. So but they've been banned. Chlorofluorocarbons are banned because we don't want to destroy our ozone. But this is the thing that's also, I think, maybe a little bit misleading, and that books need to be a little more careful about. When I was teaching public school before, I would have all these kids who were so worried about the ozone layer. They thought we were going to get a hole in it and we were all going to die, and that there was nothing we were going to do, and we were destroying the Earth. And once it was destroyed, that was it. We're all going to die. And it's misleading. Your book does say that it is created and destroyed, and this is it. Ozone is constantly being created. When that smell you smell whenever lightning strikes is ozone being created. And right now, all over the world, lightning is striking. It's raining somewhere and lightning striking, and it's constantly being replenished. So I had all these kids who were so worried that the ozone was being destroyed. And I'm like, but it's being made back again. And another thing is, it says that the hole is increasing, and that's another thing that's actually debated. That I've told you before, there's always scientists on both sides arguing about it, and there are some scientists who say that it naturally gets a hole and that it just refills and that it's nothing for us to worry about. And then other scientists are like, no, this is very, very bad. We need to fix it. So it's something you're going to have to study yourself and make up your own mind. I'm not going to tell you what to think about it, just to let you know there's more sides to it than what your book is showing at this point. And it's not, and it's scientists on different sides of this argument, not my grandpa or somebody like that. But I think we have to be careful as educators not to unduly worry kids about things that they don't have control over at this point in their lives. Like maybe later you'll be a voter and you can have more control. But for students who don't have much control, to get overburdened with worry, I think is a little bit, we need to be careful about that as educators. Just know that yes, there's a hole in the ozone, but it is being replenished constantly by lightning strikes, and that's good. And maybe there's not as big of a hole. They say in a lot of ways, because of COVID, a lot of things have sort of been fixing themselves on our Earth. So it's really interesting how quickly, COVID hasn't even been here for a year, that some things have gotten fixed. So I think my takeaway is don't overly worry about this. There's a physicist I really like. He's Dr. Paul Hewitt, and he wrote the book Conceptual Physics, and that shows you how big of a nerd I am, that I have a favorite physics textbook writer. But he has a video where he talks about that when he was really little, he wanted to be a pilot, but he didn't know how to tie his shoes, and he was so worried that the other pilots would find out and make fun of him that he didn't know how to tie his shoes. And then, of course, as an adult looking back, he was like, by the time I would have been a pilot, I would have known how to tie my shoes. So I think as people, we are very good at finding solutions to problems and finding technology to fix problems. So my idea from him a little bit is to have a little bit of faith that we're going to be able to, if the hole in the ozone is a problem, and if it's really being caused by something we're doing and not just natural, then we can figure that out and stop doing it, and we don't have to worry all the little kids about it. It'll be okay. We'll know how to tie our shoes by the time we're pilots. So I think that at this point it's not that we just don't need to be overly worried. That people are going to be able to figure out if it's not something that can fix itself, like some of these other natural things have been able to do. Okay, or you could just say, no, she's all wrong about that, and that's okay too. I'm fine with that. X-rays and gamma rays. I just didn't like seeing my kids so upset about it. I tried to calm them down always, because I had kids extremely upset. Okay, X-rays and gamma rays are the next two. X-rays are used to see bones and things inside of you. Gamma rays are used to treat cancer and also some other things like that. The next section is about radio communication, and I already told you that radio waves travel at the speed of light. There's two different kinds of radio waves. There's AM and FM. The different radio stations are given a different frequency that they transmit at, and then that's their base frequency, and then they add to it so that it's not just white noise, that it's whatever it is, that their music or talking, whatever they're doing. AM radio varies the amplitude, and that's how they have their information. FM radio varies the frequency, and that is of their carrier wave, and that is how they carry the information. And TV does them both. It uses them both. So AM can sometimes do better over long distances and around things. FM is what most people like to listen to. It's a little bit stronger and clearer. Okay, a cathode ray tube is another thing that uses these principles. It's a vacuum tube where beams of electrons are produced, and it used to be used in old TVs like the one in your book. Now we have our little flat screens, and we don't use tube TVs anymore, but they used to. But they won't even take them at Goodwill now, so they're kind of an old thing that's not used anymore, but you can read about them in the book. Telephones also take sound, change it into electric impulses that travel at the speed of light, and send it all over. We have cord phones. We have cordless phones that sometimes would use a base, but those aren't used too much anymore. Your book is old because it says there's also pagers, and nobody has those anymore. And then communication satellites can use electromagnetic radiation for cell phones and television satellites and GPS. All of those things use electromagnetic radiation to be able to move information at the speed of light, which on Earth is instantaneous. All right, so that is Chapter 12. I'm Miss Lisa. Like, share, subscribe. Come back next time, and we'll learn more science. Science is great.